Okay, I'm going to pick up right from where we left off. We just finished talking about decay factors. And before I continue sliding down, just let me point out that on that first key concept where b is greater than 1, we had a growth factor because it's growing as time increases. In this graph here, the x-axis is time. So as time goes up, on this one, the value is going up. We have a decay factor, and the decay factor, again, is that b value where the value goes down. As time goes up, the value is decreasing constantly. Okay, so that takes us down to a couple more key points for us here. It says, number 6 says, circle numbers that could be growth factors. Okay, well, we learned up here at the top that a growth factor, to have a growth factor, b has to be greater than 1. So the only answers here that we could circle would be values that are greater than 1. Okay, well that could be great. That could be a growth factor, and this could be a growth factor. So those are my only two there. Why didn't I circle 85%? Well, 85% is actually equal to 0.85 when we apply it, so that's actually less than 1. We would need something greater than 100% if we were taking the value as a percentage. And then if I'm going to circle decay factors, then we will circle the ones that are less than 1. So this one, the first one, the third one, and the last one are all values that could be decay factors. Okay, so moving right along to another application here, let's look at problem number 1. And I'll read it quickly. It says, suppose that in 1985, there are 285 cell phone subscribers in a small town. The number of subscribers increased by 75% each year until after 1985. How many cell phone subscribers were in the small town in 1994? Write an expression to represent the equivalent monthly cell phone subscription increase. Okay, it sounds like there's a lot in here, so let's just walk through what's on the paper, and then we'll learn as we go here. They've kind of gotten it set up for us. Okay, they went ahead and kind of worked it for us. They have the initial amount was 285. Okay, going back to the very top of the page, A, that's the initial amount, right? The initial amount is that A value. Okay, so in this problem, that 285 is the initial amount. All we're doing right now on number 8 is they're asking us to use the words exponent, growth factor, and initial amount to complete this diagram. Well, the initial amount was 285 because that's what they started with. They started with 285 cell phone subscribers. All right. Now, it increased 75% each year. And so you might be thinking, well, why isn't this 0.75? Well, remember, it's 100% is equal to 1. All right. So it increased by 75%. So it increased 100% plus 75%. So the new value is actually 175% compared to what it was the prior year. If you just use 0.75, you're going to have a decline because you're multiplying a value less than 1. So when we think in percentages here, we have to think 1 plus 0.75 to get the growth factor, which is what this is. This is the growth factor. Okay. Let's see, we got the exponent. This 9 right here is the exponent. Now I will need you to grab your calculator. If you don't have it, press pause and go find it. But we need to make sure that you can take this expression and correctly put it into your calculator. And if it's a scientific calculator, you should just be able to type in 285 times 1.75 to the power of 9 to get the value of 43872. You really have to have your own calculator at this point in the class. If you don't, it's going to be a tough road for you. Make sure you can put that in correctly. If you don't get that to work, bring your calculator to class and I will help you get it figured out. Okay, so that's actually the same thing that is the answer to number 9, that the number of cell phone subscribers in 1984 would be about 43872, 43,872. Okay, so again, you might need to pause and rewind that and think through it, because it is an important concept that you'll eventually have to be able to show me back there. So think it through, bring your questions to class on that part right there. If you turn to the next page, at 10 through 12, I wasn't real excited about that. I want to focus more on the next um, the next piece. So let's just go on down to this compound interest problem. I think this is really valuable for us here. It says, suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded monthly. What will the account balance be after the 12th year? Okay, let's just work through the information on the page and see if it can make sense for us here. All right, well, it says that the formula below gives the balance A. All right, so A is going to represent the current balance in the account. The balance A in an account that earns compound interest. The formula is an exponential function. Okay, so exponential function, that goes back to the y equals A times B to the x. Okay, now this strange looking equation really is the same thing as this y equals A times B to the x. The initial amount is P. That's the principal we talked about, right? The initial amount is P, and the growth factor is this 1 plus this crazy looking thing is really no more than this. This Bx is what this is. This is really like B to the x. Okay, the x is that n right there, and B is that 1 plus that right there. Now this means something. I'll try to explain it to you as we go. But the main thing is right now that you can plug in the values at this point and use your calculator to find it. All right, so here again, the principal interest, that's this right here, that's the initial amount, right? Same word we used in the previous video about y equals A. A is the initial amount, right? All right, that is P. The annual interest, okay, is this R right here. That's the interest rate written as a decimal. And this 1 right here, that's what makes it a growth factor, because it's 1 plus the interest. Now, the weird parts here is that this t up here, the exponent is n times t. That's t, time in years. And n is the number of compounding periods in a year. How many times in a year do they collect the money? Well, in this case, what did they say, monthly? So that would be 12. And that actually works out really good for us, because every month we make interest on the interest from the previous month. Works out great for us. Well, let's keep talking through this. I'm sure you're feeling confused, and that's okay, because we're just going to fill in the pieces at this point. Number 13 says, draw a line from each variable in column A to its value from the problem in column B. Okay, well, let's look at this. P, remember, that is the principal. That's the initial amount. Okay, P is the initial amount. So in this problem up here, what was the initial deposit? It was $2,000. So let's draw a line from the P to the 2,000. Okay, so that was this. All right, R, let's go back and see, what does R represent? R is right here. It's the annual interest rate. The annual interest rate. Well, what was the annual interest rate in this problem up here? If I scroll up a little bit to where I can read the problem, 4.5% interest. Now, 4.5% interest is equal to that right there. That's 4.5%, because when you divide it by 100, it goes 2 to the left. You have 0.045. So the R is the annual interest right there. N, all right, N is the time in years. The time in years that this is compounded. Okay, or I'm sorry, the number of compounding periods. I said that wrong. It's the number of compounding periods in a year. Well, since it's monthly, since N is monthly, there's 12. There's 12 compounding periods here. And then T is the number of years. All right, and in this case, the number of years was 18. All right, so T is up here to 18 right there. So with that said, what we have here is we're just going to plug those values into this equation. And this is what happens. Here's the equation. A equals P, parenthesis 1 plus R over N to the power of N times T. So we're just going to plug in those values because we want to be able to figure out how much money is in there. So A is equal to P. That's the initial amount, 2,000, times 1 plus, Okay, the interest R is the interest rate, which is 0.045 divided by N. N is the number of times it compounds in a year. That's a 12. Parenthesis to the power of, now N is 12 compounding times per year times the time is 18. So here's what you end up with. You end up with, let's simplify this just a little bit. You end up with 2,000 times 1 plus that. If you put that, just put this part here in your calculator first. 1 plus 0.045 divided by 12. You should get 1.00375 to the power of 12 to the 18, I believe is 216. Put all of that in your calculator now, and you'll get the, after 18 years, the amount of money in that account would be $4,489.01. You need to put that in your calculator, both of these, and see if you can work through the steps from here to the end. It gets a little complicated, and that's why a good calculator and your familiarity will make your life a lot easier at this point in our class. So please do that, and then come back for the next video, which you need to watch right now, and to finish the last page of our notes. And I'll be right back with that.